Welcome to Brain Vision.
So in this question, we have a particle with charge 9.45 times 10 to the minus 8 coulombs. It's moving in a region where there is a magnetic field of 0.65 Teslas in the positive x direction. At a particular instance of time, the velocity of the particle has components Vx, Vy, and Vz given in the question, and we're asked to calculate the components of the force on the particle at this particular time. So again, we're trying to find the magnetic force, which is again kind of a weird force because it is based on the cross product. So it's based on the cross product of the magnetic field, which we know is 0.65 Teslas in the positive x direction. So I'm going to write I hat here because that's the unit vector in the positive x direction. So the cross product between B and V as well. So I'm also going to write V here as a vector with the individual unit vectors I hat, J hat, and K hat, just because I find it a little bit easier to work with that way. So we've got that X component, I hat, plus the Y component, J hat, plus the Z component, K hat. So this is the full velocity written out using those unit vectors I, J, and K. Of course, you could also write it out as a tuple of 3 numbers as well. But I just prefer to do it that way. And then we can calculate the magnetic force by taking the cross product of V and B and multiplying by Q. Now, there's a couple different ways that you can do the cross product of 2 different vectors. I prefer to do it with the unit vectors as I've written here, but you also have, the method where you write out the different vectors and then you do the cross multiplication and things like that. You can do it like that, but I prefer to do it with the unit vectors, especially if one of the vectors only has one component, like B does here. So I'm just going to leave Q as Q for now so I don't have to keep writing it. And then I'm going to fill in my V and my B. So V is a bit cumbersome. I'm just going to leave out the meters per second at this point because we all know there's meters per second there. Okay, and then that is crossed with the B field, so 0.65 Teslas I hat. So what happens here when you do the cross product, you can just kind of distribute the cross product in here, right? So you're going to get Q, and then the first thing will be negative 1.68 times 10 to the 4 times the magnitude of the B field, and then that's going to be I hat cross I hat, right? Because we're taking that B field and we're just distributing it inside here. So that's going to be the consequence of that. And then we'll do this one and this one. So the next one will be negative 3.11 times 10 to the 4, 0.65 Teslas, J hat cross I hat. And then we have one more. I'll just put it on the next line here. So once you've done all of that, then you can go through and figure out what the cross products of the unit vectors is. So I hat cross I hat, anything that's, if you have vectors that are parallel and you cross them, that's always going to be equal to 0. So that kind of gets rid of that term right away. j hat cross I hat, that's crossing the y-axis into the x-axis. So let's see, that's going to give us a negative k hat. And then k hat cross I hat, that's z crossed into x, so that's going to be a positive j hat. If you haven't done the right-hand rule and cross products in a while, I would recommend to review that. Okay, so let's fill in the Q. We know that's 9.45 times 10 to the minus 8. So as I said, that first term there, that goes to 0. So we don't have to write that. And then for the second term, I'll multiply those numbers together. So that gives us negative 20 negative k hat plus $38 j hat. And then we just distribute the charge inside. So let's see. So the two negatives there are going to cancel out. So we got 9.45 times 10 to the minus 8 times 20. Okay, so doing some rounding, we get 1.19 times 10 to the minus 3 newtons, k hat. And then we'll do the same thing, 9.45 times 10 to the minus 8 times 38. And that gives us 3.59 times 10 to the minus 3 newtons j hat. Okay, so we can see that the magnetic force here has no x component. The k hat, the number in front of the k hat, that's going to be the z component. And then the number in front of the j hat, that is the y component. Okay, so this is our final answer for the magnetic field.